In this video we look at the FP1 work on polynomials. The specification gives us the requirements for this part of the module, and this leads us to the following important key facts. First of all, a polynomial of degree n will have n complex roots, provided that we count repeated roots properly. We need to know the condition for x equaling alpha to be a repeated root of the polynomial f of x, and that condition is that not only do we need f of alpha equals 0, we also need f dash alpha equals 0. Graphically, this means that at x equals alpha, the graph of y equals f of x meets the x-axis, but also has a stationary point at x equals alpha. We need to know that if f of x is a polynomial with real coefficients, and if the complex number u plus iv is a root of f, then the complex number u minus iv is also a root of f. So for a polynomial with real coefficients, the complex roots appear as complex conjugate pairs. For quadratic equations of the form ax squared plus bx plus c equals 0, if the roots are alpha and beta, then we have alpha plus beta must equal minus b over a, and alpha times beta must equal c upon a. Similarly, if we have a cubic equation ax cubed plus bx squared plus cx plus d equals 0, with roots alpha, beta and gamma, then we must have alpha plus beta plus gamma equals minus b over a, alpha beta plus beta gamma plus gamma alpha must be c upon a, and alpha beta gamma multiplied together must equal minus d over a. When dealing with root questions, these results are often useful. Alpha squared plus beta squared is the same thing as alpha plus beta squared minus 2 alpha beta. Alpha cubed plus beta cubed is the same thing as alpha plus beta all cubed minus 3 alpha beta times alpha plus beta. And alpha squared plus beta squared plus gamma squared is the same thing as alpha plus beta plus gamma all squared. Take away 2 lots of alpha beta plus beta gamma plus gamma alpha. And we'll see those three useful algebraic results being used in some of the examination examples. So let's move now on to the first of our exam examples, which comes from the June 2011 paper. So we have the Quartic equation x to the 4 minus 2x cubed minus 2x squared plus 6x plus 5 equals 0. And they've told me that one of the roots is 2 plus I, and we've got to find out all of the roots. Well, the polynomial that we're considering is a polynomial with real coefficients. So the fact that we've got 2 plus I, that's a complex root of this polynomial, means that we must also have 2 minus I as a root of the polynomial. So that means that x take away 2 plus I and x take away 2 minus I must be factors of our polynomial. And if we put those two factors together, we can say that x minus 2 minus I times by x minus 2 plus I must be a factor of the polynomial. Now there's a very simple way of multiplying those two brackets out. If we just spot the fact that both of those brackets have got x minus 2 there, so we've got x minus 2 take away I times by x minus 2 plus I, we can see that what we've really got is something of the form p minus a times by p plus a, which we know expands to p squared minus a squared. So we can say that x minus 2 take away I times by x minus 2 plus I must be the same thing as x minus 2 squared take away I squared, which then rapidly just becomes x squared minus 4x plus 4 minus 1. In other words, we multiply out to obtain x squared minus 4x plus 5. So we've seen that 2 plus I being a root means that 2 minus I is also a root, and those two things together tell us that x squared minus 4x plus 5 must be a factor of the polynomial. So we can now try and finish the factorisation of the polynomial. So we've got x to the 4 minus 2x cubed minus 2x squared plus 6x plus 5 has got a factor of x squared minus 4x plus 5, and we've got a second factor that we need to try and work out. Well, first of all, the second factor must start off with an x squared to make sure that we've got the x to the 4 term when we multiply things out. The next thing that we can observe is that the second factor must end with plus 1, because when we multiply things out we've got to end up with plus 5. So plus 5 times plus 1 gives me the plus 5 that I've got. The only bit that we're in any doubt about is what goes in the middle. So let's at the moment suppose that we've got a middle term which is just something times x. I've called it a times x. What's the value of a? Well, we can work that out fairly easily by looking at the x cubed terms. Now the x cubed terms are going to come from x squared times ax, but also from minus 4x times x squared. We want there to be minus 2x cubed. So we've got minus 2 must be, the minus 2x cubed must come from the a times x cubed take away the 4 times x cubed. So we must have minus 2 equals a minus 4. In other words, a must equal 2. So we now have a full factorisation of the polynomial. And if we look carefully, x squared plus 2x plus 1 is of course just x plus 1 squared. So we've got a full factorisation of the polynomial now. We know that x squared minus 4x plus 5 gives us the roots 2 minus I and 2 plus I. X plus 1 squared is just going to give me x equals minus 1 as a root. So there we are, we've got now our roots are 2 plus I, that was the given one, 2 minus I, and then finally we've also got minus 1 as a repeated root. Now if we look at the marking for this question, the first mark was simply for observing that 2 minus I had to be a root. We then had to establish the fact that x squared minus 4x plus 5 was a factor. That gave me 2 marks. Then obtaining the fact that x squared plus 2x plus 1 was also a factor, obtained the next 2 marks. And then finally, for the final 2 marks, we just had to observe the fact that that meant that the final root was x equals minus 1. So 7 marks for that question. Moving on to the next question, which comes from the June 2010 paper. We have a quadratic equation, and the quadratic equation is x squared plus 2x plus 3 equals 0. The roots of this quadratic equation are alpha and beta, and we have to find the quadratic equation whose roots are alpha minus 1 over beta squared and beta minus 1 over alpha squared. Well, for a quadratic equation, we know that alpha plus beta is always minus b over a. So in this case here, we've got alpha plus beta is minus 2 divided by 1, which is minus 2. And we've also got that alpha times beta is always c upon a, which in this case is 3 over 1, which is 3. So we know that alpha plus beta is minus 2, and we know that alpha times beta is 3. So let's now suppose that the equation we are looking for is the equation ax squared plus bx plus c equals 0, with a, b and c being capital letters this time. Now, we know the roots of the equation are alpha minus 1 over beta squared and beta minus 1 over alpha squared. So the sum of the roots must be minus b over a. So alpha minus 1 over beta squared plus beta minus 1 over alpha squared must equal minus b over a. Let's tidy that up slightly. We've got minus b over a must be alpha plus beta, take away 1 over beta squared plus 1 over alpha squared. Well, you already know the value of alpha plus beta is minus 2, so I'm not going to worry about that bit at all. We need to have a think, though, about what we can say about the value of 1 over beta squared plus 1 over alpha squared. So 1 over beta squared plus 1 over alpha squared, well, we're adding two fractions. The sensible way of adding two fractions is to use a common denominator, so we can say that that's the same thing as alpha squared plus beta squared all over alpha squared beta squared. Alpha squared plus beta squared is the same thing as alpha plus beta all squared, take away 2 alpha beta. Now that's one of those useful little results that we commented on the key facts page. And the denominator, which was alpha squared beta squared, can be rewritten as alpha beta all squared. Now, we know the value of alpha plus beta, we know the value of alpha times beta, so we can work out the value of 1 over beta squared plus 1 over alpha squared. So that is minus 2 squared take away 6 divided by 9, which is going to lead me to minus 2 over 9. So I've now know that minus b over a is the value of alpha plus beta, which is minus 2, take away the value of 1 over beta squared plus 1 over alpha squared, which is minus 2 over 9. So in other words, we've got minus b over a equals minus 16 over 9. Or in other words, b over a is 16 over 9. So we've got an expression for minus b over a. We can do the same thing to try and get an expression for c upon a. So c upon a is the product of the two roots. So c upon a must be alpha minus 1 over beta squared times by beta minus 1 over alpha squared. Multiplying the brackets out, we get alpha beta minus 1 over alpha minus 1 over beta plus 1 over alpha squared beta squared. So that's alpha beta, take away 1 over alpha plus 1 over beta, add 1 over alpha beta all squared. We can deal happily with alpha beta. We can deal happily with 1 over alpha beta squared. We've just got a little bit of work to do to work out the value of 1 over alpha plus 1 over beta. And again, we just need to do that by putting a common denominator into play. So that's the same thing as alpha beta, take away beta plus alpha over alpha beta, plus 1 over alpha beta, all squared. We know that alpha beta is minus 2. We know that alpha beta is 3. We know that alpha plus beta is minus 2. So we've now got an expression for c upon a, which can be easily evaluated to give us 34/9. So, the equation we're looking for is the equation ax squared plus bx plus c equals 0. We know that minus b over a is minus 16/9. We know that c upon a is 34/9. And if we simply choose capital A to equal 1, then we've got b must be 16/9, c must equal 34/9, which means that the equation that we're looking for is x squared plus 16/9x plus 34/9 equals 0. Altogether there were 8 marks to this question. First mark was simply saying the value of alpha plus beta had to be minus 2, together with the value of alpha times beta had to be equal to 3. There were then 3 marks for obtaining the value minus 16/9 for the value of minus b over a, and then another 3 marks for obtaining the value of c upon a, and then finally an answer mark for obtaining the final quadratic equation. Our final example comes from the January 2011 paper, and we're moving up to a cubic equation this time. So we've got the equation x cubed minus 3x squared plus 2x plus 4 equals 0 has got roots alpha, beta and gamma. And the first thing we've got to do is we've got to show that beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma must equal minus 7. On questions like this, it's always a good idea to start off by writing down what we know about the roots. So we certainly know that alpha plus beta plus gamma must be equal to minus b over a, so that must be minus 3/1, so that is 3. We also know that alpha beta plus beta gamma plus gamma alpha must be c upon a, which is 2. And finally, we know that alpha times beta times gamma must be equal to minus d upon a, which is minus 4. It's always worth getting those 3 facts down straight away. Okay, so we've got those 3 results down. We've got to think about this rather nasty expression here. We're adding 3 fractions, so the sensible thing straight away is to move to a common denominator. The common denominator is going to be alpha, beta, gamma. So the first fraction, we've multiplied the bottom by beta gamma. We need to do the same to the top. So the first fraction, when we've put it over the common denominator, is going to be beta squared gamma squared over alpha, beta, gamma. The second fraction, we've got gamma alpha over beta. We've multiplied the bottom by alpha gamma. We need to do the same to the top. So that's going to be gamma squared, alpha squared. The third fraction, we had alpha beta over gamma. We've multiplied the bottom by alpha beta. We need to do the same to the top. So that's going to give me alpha squared, beta squared. Now, if we remember that p squared plus q squared plus r squared is the same thing as p plus q plus r all squared, take away 2pq plus qr plus rq. That again is one of those useful results on the key facts page. Then we can say that beta squared gamma squared plus gamma squared alpha squared plus alpha squared beta squared is the same thing as beta gamma plus gamma alpha plus alpha beta all squared. Take away 2 lots of beta gamma gamma alpha plus gamma alpha alpha beta plus alpha beta beta gamma. Now have a look at that second bracket there. You'll see each of the terms have got a common factor of alpha, of beta and of gamma. So we can rewrite that second term on the right hand side as 2 lots of alpha beta gamma times by alpha plus beta plus gamma. Now we know the value of beta gamma plus gamma alpha beta. It's 2. We know that alpha beta gamma is minus 4. We know that alpha plus beta plus gamma is 3. So we've got the value of beta squared gamma squared plus gamma squared alpha squared beta squared must be 28. So moving back up the page, the top of my fraction is worth 28. The bottom of the fraction is minus 4. So we have got beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma must be minus 7, which is the result that we wanted because of the working that we've got underneath there. So we've done the second part of the question. And now finally, the question is asking me to find the cubic equation whose roots are beta gamma over alpha over beta, alpha beta over gamma. So let's suppose that the required equation is ax cubed plus bx squared plus cx plus d equals 0. Then we've got minus b over a must be the sum of the roots. So minus b over a must be beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma, which must be minus 7. So there's part A straight away coming into use to enable us to answer part B. C upon A must be the sum of the products of the roots. So we've got the first root times the second root, beta gamma over alpha times gamma alpha over beta, plus the second root times the third root, that's the first root times the third root, beta gamma over alpha times alpha beta over gamma, plus then the second root times the third root, gamma alpha over beta times alpha beta over gamma. And when we look at that, it very rapidly simplifies down to gamma squared plus beta squared plus alpha squared. Going back, we're going to use one of our key facts again. That's the same thing as alpha plus beta plus gamma all squared. Take away 2 alpha beta plus beta gamma plus gamma alpha. So that is going to be 3 squared, take away 2 lots of 2. So that gives me 5. And finally, we need to move and look at minus d over a is the product of the 3 roots. So that's beta gamma over alpha times gamma alpha over beta times alpha beta over gamma, which rapidly simplifies to being the same thing as alpha beta gamma. So we've got minus d over a must be simply minus 4. So if we put a equals 1, then b must be 7, c must be 5, and d must be 4. So the equation that we're looking for is the equation x cubed plus 7x squared plus 5x plus 4 equals 0. Now this question actually took 11 marks. The first 2 marks were for correctly writing down the values of alpha plus gamma plus gamma alpha plus alpha beta, and alpha beta gamma for the original equation. And then the next 3 marks were for obtaining the expression for beta gamma over alpha plus gamma over alpha. For obtaining part A, beta gamma over alpha plus gamma alpha over beta plus alpha beta over gamma, and check or verifying that it does come out to be minus 7. There were then 3 more marks for working out the value of C upon A and obtaining that value of 5. There were 2 more marks for obtaining the fact that minus D upon A had to equal minus 4. And then the final mark was for obtaining the cubic equation. And that's the end of our final question.